Hello, everyone, and thank you for joining us today. My name is J.C. Hernandez, and I'm a tech transfer analyst at NASA Johnson Space Center. I'll be your host for this NASA Technology Transfer Program webinar on the human-powered ventilator. Our presenters today are Dr. James Locke and Ms. Holly Newton. Dr. Locke has been a flight surgeon at NASA Johnson Space Center since 1999. He is currently engaged as the lead physician for the ongoing astronaut selection process. He served as a crew surgeon for multiple space shuttle missions, as well as for multiple long-duration crews aboard the International Space Station. He is currently assigned as a physician at the Johnson Space Center Flight Medicine Clinic. He's the lead physician for medical informatics at JSC and is the lead physician for the Lunar Gateway program. Holly Newton is an aerospace engineer working for NASA Johnson Space Center as a lunar hardware designer and developer in the Crew and Thermal Systems Division. She's been with NASA for 2 years, following 3 years in the NASA Pathways internship program, where experiences related to human spaceflight have included work with mission control, crew and thermal systems, trajectory planning, and spacecraft structures. Newton was the lead mechanical designer on the NASA team that developed the human-powered ventilator design for use on long-duration space missions and to assist with shortages of electrically powered ventilators on Earth. At this point, I'm going to turn it over to you, Dr. Locke and Ms. Newton.
Well, good afternoon, everybody. My name is Jim Locke. As pointed out, I'm one of the flight surgeons at NASA Johnson Space Center. And Holly and I at Newton work here together on various projects. Just as a little bit of background, we began this work several years ago with our upcoming Artemis Orion missions. Some of my physician colleagues thought that it would be necessary to have a means of providing mechanical ventilatory support for critically ill astronauts. The difficulty with that with the Orion spacecraft is very limited power. So a mechanically, electrically powered ventilator was not really something on the table. And so Holly and I got together and developed this technology. And I guess we'll move on to the next slide. So the thing at NASA is that we oftentimes, we develop our own technology, but it has uses, potentially great uses in the terrestrial world. And NASA's human space missions have many analogies to resource-poor areas on Earth. When you think about the problem that causes, much of the world lacks access to advanced medical care. Somewhere between 700 million and 1.3 billion people on this planet lack reliable access to electricity, and so it's not possible for them to have advanced diagnostic or treatment capability that relies on electrical power in these environments. And so the critical care capabilities that we take for granted in the developing world simply are out of reach for hundreds of millions of people. And just like we considered in the human space program, in a resource-poor environment, medical conditions that lead to compromises in respiratory functioning can't be treated. Now, the big cause of respiratory failure that we've all seen recently is COVID. And initially, there were a lot of people that were filling up ICUs throughout the world, and there was an actual shortage of mechanical ventilators, even in the developing world. But there are many other causes of respiratory failure that happen all the time. And also, there are patients that, not for respiratory reasons, need to be put into a medically induced coma, and when you do that, they lose their ability to breathe spontaneously and they need mechanical ventilatory support. So if you just consider thousands and thousands of people die every year because they lack access to ventilatory support. And at the bottom of this presentation, you can see a link that touches upon the scope of the problem of the lack of advanced medical equipment in the developing world. Next slide. So when you think about mechanical ventilation, there are a number of sub-functions that you need to achieve that. The first and very challenging one is inserting the invasive airway, some type of breathing tube, and that needs to be managed by skilled clinicians. And those are quite uncomfortable. And so patients need to be sedated. But once they're sedated, they stop breathing and they need a mechanical ventilatory support device. And so these mechanical ventilatory support devices have fairly simple requirements. They have to deliver pressurized air or gas into the patient's lungs. People breathe between 300 and 600 and 700 cc's per breath. That breath needs to be delivered pressurized to 10 water. And people breathe 10 to 20 times every single minute, every hour of every day. And so back during the COVID time, there were all sorts of reports about people that want to come up with innovations to provide pumps and things and fans that could meet this need. And creating pumps and fans that can deliver air in that fashion is pretty easy. The part that was neglected is that these systems require very complex feedback control and adjustment capabilities. Because if it doesn't, the systems will very quickly go awry and they'll stop working correctly and the patient will die. And that's really the trick of this. Next slide. So basically there are two types of mechanical ventilators, automated and manual. The automated ventilators are the ones that you see on television, you see in ICUs. They are very easy they're much easier to manage with less personnel, but they require reliable electricity. They have very complex sensors and control software. They're very difficult to maintain. And their operator requires very specialized training. And they're very expensive. On the other hand, there are also manual ventilators that are available. You can see a picture of the standard bag valve mask. We use them in hospitals for short-term resuscitations. They don't require any electrical power. They're very simple. It takes relatively little training to be able to operate them, and they're very cheap. The problem with them is that they use the very small muscles in your hands and wrists. You can only use them for a few minutes before your hand becomes so fatigued that you just can't go anymore. Next slide. So as I talked about, back in 2017, Holly Newton and I worked on the development of this ventilator for the Orion spacecraft. And we made a prototype, and then for various reasons decided to shelve the project at that time. But in 2020, during the pandemic, NASA decided to revive the project as a compassionate use in hopes of helping potential COVID-19 patients when the ventilators were in short supply. And we wanted to come up with something that was human powered, that was simple, easy to operate, had the same minimal training requirements, but could be used for longer periods of time than a bag valve mask, had to be inexpensive and simple to manufacture. And so with that, I'd like to pass this off to Ms. Newton.
Thank you. So to meet those requirements that Dr. Locke just talked about, this is what we came up with for our design. So on the right here is a rendered image of a 3D model that we created. And it utilizes a hand pumping motion to open and close these two panels. And there's a bellows in between the panels that takes air in and then pushes it out to the patient. It maintains some of the characteristics of existing manual ventilators, so you can physically feel the air. You have some tactile feel, so you can determine how fast and how much air are you giving to the patient. It does not require sensors, which reduces the complexity and the cost greatly. But if you wanted, you could add sensors in line with the tubing that goes to the patient. So you could add air pressure or flow sensors just to help the operator. It could be used with attachments to supply extra oxygen, and it has some locations on it to put straps so that you can strap it to your leg or strap it to a table to give you some stability and help you hold it. And then it can be used with intubated patients, or it could be used with masks, like a bag valve mask is used. So this video kind of shows the operation of it. So you just open and close it to open the bellows and bring air in, and then close it to push it away. So this is kind of the airflow, and I actually do have a 3D model of it that I'll try and use to help talk about this. So the idea is that from one end of your hinges, you would have it open to surrounding air or attached to an oxygen bag to supply that air. And then it goes through inside, there's a channel, an airway for the channel. And then on each of the halves of this panel, as you can kind of see in the picture on the right, there's this like crosshair design. And in here sits a flutter or check valve, so that when you open the device, one of the check valves on one side will open up, let air flood the bellows, and then as you push it closed, the one on this side will close, and then the check valve on the other side will open to let you, as you squeeze it closed, let air flow through the other panel and out to the tubing that's connected to the patient. So some of the features of this device is that it could have a torsion spring or some type of spring in the hinge to help reduce the load on the operator. So that would allow it to automatically kind of pop open. So all the operator has to focus on is closing it. But it would also need to be a light enough force so that it doesn't mask the tactile feel, so that you can still tell how much air you're giving to your patient. It has holes on the side here for the straps that I talked about. So you can strap it to your leg if you're standing up. You can strap it to a table or something just to help kind of hold it and reduce the load on the operator. And then in the right picture here is a prototype of a potential bellows. So it is a silicone accordion-shaped bellows that is used to perform this function. So this design is conceptual. So it still requires some additional work to meet medical requirements and also to meet mass manufacturing requirements. We've done some 3D printing of different prototypes, and we've tried them out to test out that airflow path and see that that works. But 3D printing is not the most effective mass manufacturing process. So something like injection molding would be a better process, we believe, for making this ventilator. And we were able to partner with some volunteers from local and international academic, philanthropic, and business organizations to help us explore potential design improvements. So we were able to take the original concept and create a couple other iterations to figure out a better way of doing this process and making this device even easier to operate. Currently, there is a pending patent on this device, and this device has also won an award from the Federal Laboratory Consortium. So we won a regional award for notable technology, and we're also nominated for a national award. So what are the main benefits of this device? So we believe that this device improves upon the existing manual ventilators by making it this push-pull motion to open and close it, making it less fatiguing on the operator. So it allows you to use it for longer durations of time. That, I think, is one of the key benefits of this device, is the bag valve mask works great, but that squeezing motion, you just can't do it for a long, long time. And this open close motion is much easier on your arms and reduces the load on the operator. This design also maintains the benefits of existing human-powered ventilators. So it's low cost, simple to manufacture, it's easy to operate, it's pretty intuitive, so it doesn't require a lot of training. It doesn't require sensors, but sensors could be added to further assist the operator. It's portable in size, easy to ship. It can also be cleaned or washed for reuse, or it could be made into something that's disposable, so you don't have to worry about maintenance efforts on it. And it doesn't require electricity, which can be helpful in a lot of different scenarios. So, for example, we think that this would have great applications in space exploration. So if this product were to become something readily available in the market, the space industry would probably be one of the customers as we look forward to longer duration missions to Mars and further beyond. This would be a product that would be of great interest to the space industry. But it would also be useful in emergency situations and emergency response vehicles, could be used in hospitals that are facing high demand, and maybe the automated ventilators just aren't available at a certain time, so they need to maintain some long duration ventilation on a patient until an automated ventilator opens up. And it could be used in resource poor areas of the world, places where electricity just isn't readily available or isn't reliable. So we believe that there's a lot of different applications for this device and that it could be a life-saving technology. Dr. Locke, before I go into the last slide, was there anything else you wanted to add that I missed?
No, I think you've covered everything quite well. Thank you.
Perfect. So with that, that is our design. And I'll open it up for questions, and just know that this design is available for licensing. We would love to see this design out in the world and out there helping save lives.
Once again, we really appreciate you taking the time to be with us. Thank you, Ms. Newton, and thank you, Dr. Locke. I'm J.C. Hernandez. Have a great rest of your day.